Hi, today we're going to cover Chapter 3, which is titled Molecules, Compounds, and Chemical Equations. I'm not quite sure why they use the chemical equations in the title for this chapter. It's not covered in this chapter. We're talking about formulas and naming. However, that's what the book says. So here it is. Now, before we get started, you of course want to make sure that you've also printed out the notes that I've prepared for this session, and it's going to have all the problems that we work out here as examples. And there's also going to be a homework assignment that pairs along with this as well, so look for that attached with this video somewhere. You're also going to want your periodic table to be out and handy, as we're going to reference this several times throughout the video today as well. Let's get started. So to start us out, we're going to recap what we've talked about previously, and that's mixtures and compounds. So a mixture just means different substances are in the same container. So on the left, we see a balloon. In this balloon, we have hydrogen and oxygen. And so you'll notice the colors are going to be consistent throughout the textbook and throughout models that are used, like you've seen me hold up before, my little water molecule. So again, we have red for oxygen and white for hydrogen. And so you can match this to the pictures you see on the screen and see how they match together. And so that's done on purpose. So what do we have in that balloon? I see two oxygens stuck together and two hydrogens are stuck together. So those are each pure substances by themselves, just hydrogen, just oxygen. They just so happen to be in this balloon together. So they are separate substances. They are a mixture. And so here's a different model kit I have that I'll be using throughout the video as well. So each of these atoms are what we call diatomic, meaning two atoms. And there are several elements that do this. We'll go over it in the course of this video. Hydrogen and oxygen are two of them. So that's a mixture. A compound is when we have different elements bonded together chemically. And so I'll refer back to this model because here we have these sticks that are here and here. That represents the chemical bond that is being shared between these atoms. Okay, the compound picture that you see on the slide is more representative of using this model. This is called a space-saving model when you see it like this with no sticks. Okay, but a compound is that chemical bonding. So how does that occur? Well, I could spend a whole hour just on this. But just briefly to get you, the information you need for this chapter, we have our nuclei in the center of each element. And in that nuclei, we have not only neutrons, but our positive protons. And our positive protons, being both positive, are going to repel when they get close to each other. So let's look at this diagram down the bottom, and then I'm also going to hold up my two oxygen atoms since they're larger than the hydrogen. And you can see how this would superimpose on that image that's on the slide pretty nicely, right? So what do we have? We have the tiny, tiny nuclei, which would be the size of a small pencil dot for the scope of this model. The nuclei would be just a pencil dot inside the center where our protons and neutrons are. The whole model that we see is actually representing the outermost electrons that are used in bonding. So we're actually seeing the electrons interact with these spheres and the one you see on the screen. So let's talk about magnets. You know that opposites attract. Positive attracts negative, negative attracts positive, okay? But if the same charges are near each other, they will repel. So that's what's keeping this bond together. If we look at the image on the screen, you could see that X, that cross that's in the middle there where it says repulsion. And so it's pointing, let's look at it horizontally first. So horizontally, it's pointing from one proton of one atom to the proton within the second atom. And so they're going to maintain a certain distance away, because if they get too close, they're going to repel, the molecule falls apart. Likewise, if we look vertically, we see the repulsion arrows in this direction as well, but there at each end of the arrow, it's pointing to an electron. See the little negative sign? And so that would refer to the electrons that are going around actually making this connection, this bond. If the electrons from each atom get too close to each other, that will repel as well. They're both negative. And so the electrons are always moving around very, very fast. So that hardly happens, but we could, I suppose, if we had a camera to do super, super, super slow motion, and we focused on two atoms paired together like this, we would see it kind of go like this because of that repulsion and then attraction of the opposite charges keeping them together. Okay, so that's a brief chemical bond intro, just to give you an idea of what's happening. But then we're going to classify this into two different types. We're going to talk about molecules of each type of bond. Then we're going to talk about naming and formula writing for each as well. And so these are the two types, ionic and covalent. Now, covalent can also be called molecular. So just an awareness, I flip back and forth when I use both terms. So covalent and molecular mean the same type of bond. Okay, we'll talk about ionic first. So here we have our periodic table. Okay, and you know from the last chapter that the majority are metals. From about here over to the left are all metals. Okay, and then the nonmetals are concentrated just up in this top right corner. So an ionic bond is when we'll have one element from the metal portion of the table bonding to an element of the nonmetal side. So that's how you can tell it's ionic. It's one from each side of the periodic table. So metals will lose electrons all the time. They become a positive ion, which we call generally cations. The nonmetal always gives up its electron to that other element, and it becomes the negative anion. So the cation becomes the positive ion, and then the nonmetal gaining that electron from that metal becomes negative, and we call that generally an anion. So the oppositely charged ions will form this ionic bond. Okay, so ionic compounds always form in a structure like this, and I have the model that matches. So this matches the drawing down there, so you can see it in 3 dimensions. So this is called a crystal lattice. Okay, all ionic compounds form crystals, which is this kind of interconnection between one ion and the next. And it's because of that opposite charge. So if they hold these charges, they're going to keep attracting the opposite charge so as long as those ions are in the area. So it ends up building and building and building, and we get these crystals. Now, they don't always look like this. They can be different sizes between the ions. They can be, kind of twisted of each other. If I kind of, twist and angle it that way so it's more like a rhomboid versus a perfectly squared off square. It can do things like that, but the connectivity is the same. I also want to point out, though, with that word connectivity, these aren't physically connected like these lines, these sticks illustrate in the drawing and in this model. That's just to hold them in place. Obviously, they can't float. And to draw them, it's just to show how they are associated with each other. But with ionic bonds, they are not physically connected. It's just that, let's call it a magnetic type attraction that holds them near each other. That might be more accurate to say. So in this slide, there is a YouTube clip. I highly encourage you to check it out. It's not long. It's probably with 10 minutes or so. And that little popcorn icon is a bit of a foreshadowing as to what they're showing, but it's this reaction that we have underneath here. So sodium metal, if you take a look at the far left, sodium is a metal when it's a pure element, and it will look like the purple spheres that you see there. A solid always has that arrangement of closely packed atoms. Okay, these are atoms here, they're neutral. And then we have our chlorine gas, which you can see, like the previous slides, the very beginning, where we saw the hydrogen separate and the oxygen separate. Chlorine, being green, is also diatomic. So this is hydrogen, the white, and chlorine is represented by green. They are both diatomic when they are just their pure element selves. Okay. So what is the story? How does the story pan out? So the sodium is a metal. On our periodic table, we can find it in group 1A. Because it's in group 1A, it'll always lose one electron and form a +1 charge. So what you could do here is above the 1A, you could write +1 right there, because all of the elements in this group 1A behave the same way. They all will form +1 when they form an ion. Okay, we could go quickly through the rest. 2A always forms a +2. Then we come over here. Group 3A forms a +3. Group 4A is actually in between. It's right in the middle between 1 and 8. So we don't have ions form here. They will be sharing in this case, so there's no plus or minus there for 4. But then we come to 5. 5 is 3 away from 8. We're on the nonmetal side where they become anions. So group 5A will form a -3. Group 6A is 2 away from 8. So group 6A will form a -2 charge. Group 7 is just 1 away from 8, so it'll form a -1. And finally, 8A does not have a charge because those are the noble gases. And so sodium is going to give up its 1 electron to the other element, in this case chlorine. Since in the beginning sodium was neutral, it had the same number of protons and electrons. So the number of plus and the number of minus were the same. They canceled out with no charge. That's called neutral. But it lost an electron. So it has more protons now than electrons by losing one of those electrons. So it now is a positive ion. Here it is. And yes, it gets smaller. More on that later. Okay. The chlorine was neutral. Same number of protons and electrons. So it was no charge as well. But when it takes up the electron from sodium, it now has more negative electrons than it does protons. So it gets a negative charge. There's only 1 electron moving, so the charge is a -1 for chlorine and a +1 for sodium. And so as long as there are atoms around in this container where this reaction over here, sodium and chlorine, is taking place, you will keep building and building and building and building because of these charges. And that's how you get the crystal. Okay, so, looking at these pictures that are on the far left showing you the atoms as they are in those substances, the solid metal and the gas, there's millions and billions and trillions of atoms there to be used in this reaction. So they just keep building and building and building on and making these crystals. And finally, you see the microscope view of table salt, which is what we made, sodium chloride. All right, the other type of bonding is covalent or molecular. And we can branch this down into 2 types as well. Let's start with what type of element we see here. So ionic was a metal and a nonmetal. Covalent is when we have more than one nonmetal come together. It's going to be 2 or more. And again, the nonmetals are just located in this top right corner. So we don't have as many elements to choose from. When we were able to use the metals, we could use most of the table. but now we're restricted to the elements just up in this top right corner, group 5, 6, 7. And so what can we form with that? Well, the molecular that we see here on the left, that's carbon dioxide. And when carbon dioxide is a molecule and a solid, see, it makes dry ice. So I'm just building a couple here. Okay. So I have one carbon dioxide molecule right here, and I have a second one here. If it's a solid, the particles get close together, and so they just kind of settle, and it starts to form a solid. Think of an ice cube, okay? And when we heat it up, they start to separate from each other. We get a liquid, and then heating it up more, we'd get a gas, and so on. But they are individual molecules. That's CO2. C is black, and O is red, okay? Now, if we look at the network covalent, which is shown as an example on the right, we have silicon dioxide, but it looks like an ionic crystal. The difference is we have a physical connection here with covalent. Ionic was that magnetic kind of association between plus and minus. With covalent or molecular, we do not have plus and minus charges. There's a sharing of electrons here. And so this is just one type that forms. We call it a network, and it's just a big molecule. Still the same ratio, though. I want to focus your attention to the bottom where we have the molecular formulas. Solid CO2 is 1 carbon and 2 oxygens. That's one molecule of it. Same with silicon dioxide. One atom of silicon is connected to 2 oxygens, and that is one molecule. It's just how they arrange each other is different. They are both covalent, but they're arranged a little differently when they come together. So here we get to conceptual question connection number 1. This is in your packet of notes. So let's take a minute. What type of bond, would it be ionic or covalent, forms between nitrogen and oxygen? All right, let's see if you were right. If you said covalent, you're right. Nitrogen and oxygen are both nonmetals. Okay, so let's briefly go over the chemical formula so that we're all up to speed with that. So a chemical formula is going to tell you which elements are present, and it's also going to tell you how many atoms of each of those elements are bonding together to make that substance. So we know that water is H2O. Again, my model. Okay, so H2O means that for every water molecule, I have 1 oxygen and 2 hydrogens. If I have that combination, I have water. Sodium chloride, the formula is NaCl, because if we look at sodium chloride, for every 1 sodium, there is 1 chlorine. Carbon dioxide. Okay, carbon dioxide, 1 carbon for every 2 oxygen. And CCl4, okay, so a little limitation here. So my model kit, I only have 2 chlorines that came with it. So I'm going to make it with hydrogens. Imagine all the white are green for chlorine, but this would be CCl4 or carbon tetrachloride. All right. There's a lot in this chapter, so if you need to stop the video, come back later, or review sections of it, you may need to do that with this chapter because of the amount of material. So now that we've talked about types of bonding and we've talked about formulas, we can now separate formulas further into 3 different types. They each have their uses and their favorability. So let's talk about each of these. The 3 types are called empirical, molecular, and structural. Okay, just going to slide my picture down. So an empirical formula tells you the relative number of atoms of each element in a compound. Another definition for this would be an empirical formula tells you the lowest whole number ratio of elements to each other in that substance. Okay, the lowest whole number ratio. The molecular formula is the actual number of each element, the atoms that come together and make that substance. So let's pick apart these two types. So for A, that first example, H2O2, let's build it. Okay, so I have H2O2 right here. Still getting used to the camera. Right, there we go. Okay, and so H2O2, the actual formula says I have 2 oxygen, which are the red, for every 2 hydrogen, which are the white. And that is the molecular formula. This is H2O2. And you probably have some of this in your home as well as the water. This is hydrogen peroxide. Okay, the empirical formula is the lowest whole number ratio of each element. And so if I have 2 of each, I could mathematically reduce that, right, and say not every 2 oxygen there are 2 hydrogen, but for every 1 oxygen there is 1 hydrogen. So looking at the subscripts here, you would look at those and say, can you reduce these 2 numbers? If you can get an empirical formula. So reducing the 2's to 1's gives me an empirical formula of HO. HO is not hydrogen peroxide. Hydrogen peroxide has to be H2O2. That's its molecular formula. Okay, let's look at the next one. So the next one we have boron. We have 2 atoms and 6 hydrogens connected together. That's that particular substance, its formula. Can we reduce this? Yes, I can reduce both of these numbers, the 2 and the 6, by 2. So when I divide 2 by 2, I'll get 1. So here's my 1 boron. When I divide the 6 by 2, I'll get 3. Here's 3 hydrogen. So the molecular formula is B2H6. The empirical would be BH3. And finally, let's look at the third one. So this is CCl4. Okay, that's the one I built on the last slide using hydrogens for chlorine. Okay, so there are 4 white dots there. If I can get my hand out of the way. Okay, right there, you can see them all. And so with this, there's for every 1 carbon, there are 4 chlorines. Well, we can't reduce 1 and still have a whole number. So when we have this situation, the molecular formula and the empirical formula have to be the same. Remember, it has to be a whole number ratio for that empirical. All right, so again, this slide just shows the definitions. Again, you have a spot for that in your note packet that goes along with this video. The empirical formula, I would prefer you write down the lowest whole number ratio as the definition for empirical. Molecular is the actual number of atoms for each element that make up that substance. So here's just a picture view. This chemical is named ethene. The molecular formula for it, the actual formula, is 2 carbons, 4 hydrogens. Okay, the empirical formula is the ratio of that. So you look at the 2 and the 4 and say, can I reduce both of these? You have to be able to reduce all the elements by the same number. I can reduce the 2 by 2 and get 1. I can reduce the 4 by 2 and get 2. So the empirical would be the lower ratio. All right, example 1 in your note packet. Write the empirical formulas for the compounds that are represented by their molecular formulas. So these are the actual, you're giving me the ratios. You can go ahead and stop the video, try it out, and then we'll see how you did. Okay, so here's example 1. Let's go through the solution. So for C4H8, the largest number that would divide in both 4 and 8 would be the 4. So we're going to reduce this formula by dividing 4 by 4 and getting 1, so 1 carbon, and dividing 8 by 4 and getting 2 hydrogen. Empirical is CH2, molecular is C4H8. For B, we have B2H6. The largest number that I could divide both of these by would be 2. So dividing 2 by 2, I get 1 for boron. Dividing 6 by 2, I'll get 3 for hydrogen. BH3 is the empirical formula. B2H6 is the molecular formula. And finally, not sure why the textbook did this, but this was the exact same example we gave for keeping the empirical the same as molecular. So we're seeing that a second time. Okay, the last type of formula is structural. And so just as the word hints at, this is showing the connectivity, the physical arrangement of the atoms. So saying H2O may not conjure up the image of an oxygen being in between the hydrogens, right? Because the H's were together, H2. So why isn't it like this, where the 2 hydrogens are first and then my oxygen? Okay, so the structure tells us the actual connectivity of the atoms to each other. And so on the bottom there, you see our hydrogen peroxide again, our H2O2. I can actually build that with the sticks here. There we go. Okay, so there's my H2O2. Now take a look. It's written 2 different ways at the bottom of the slide. One way is just writing it in a straight line. The lines represent where the bonds are, which resemble a pair of electrons, 2 electrons that are being shared between those atoms. Okay, the lines here in the model are translated to these sticks. When I put this together, the only result that can occur is this structure because of how the holes for each element are drilled. Okay, so it happens that the molecule kits are precision cut so that for each element, when you bond it, it's making the correct bond angles for that element. So this is the true structural formula for hydrogen peroxide. This shows the connectivity and the bond angles. Those are things we'll cover in depth in a later chapter. But for now, the structural formula just has to show the connectivity. Okay, we don't learn about geometry until another chapter, so I'm not going to hold you to know it now. Okay, so both of these structures are correct with the bonding. And so we'll also go through in detail why the 2 oxygens are next to each other and why I can't have hydrogens together. So stay tuned. All right, why do we use one formula type over another? Well, it depends on what we're trying to say. What type of information are we trying to give out? So structural formula, you want to remember, I put it in red there for you. Structural is always going to give you the most information because if it's geometry, that's very specific on how things are connected. Even if it's just the linear connection that you saw on the previous slide, just showing it's H to O to O to H, that is still giving you more information than just a empirical or a molecular. On the other side of that scale, the empirical is always going to give you the least amount of information because it's just a ratio. There can be many compounds that have different molecular formulas but share the same empirical because it's a ratio. All right, so here we are at conceptual connection number 2. Out of these pictures, what do you think is the correct structural formula for water? All right, if you picked C, you would be correct. Okay, that is a structural formula for water. However, with the geometry, water does not form a straight line like that. It forms this structure. We call this bent. where this angle here between the hydrogens and the oxygen, this is 120 degrees all the time. Okay, so the model kit, it does talk about this in the textbook, so here's where it mentions that on how the elements are represented by the same color all the time. And you've seen the two different types of model kits that I have here, and it's across the board. Oxygen's always red, hydrogen's always white. Chlorine or any group 7A halogen is green. Nitrogen is represented by different shades of blue. Phosphorus, I've seen it as purple. It looks kind of a dark blue here, but sulfur is always yellow. And these are our more common elements that bond together to make common molecules that we would build with kits. We don't see many compounds forming with the transition metals here in the middle, and so they're usually not represented in model kits. Okay, so the molecular models, we have a third one, which actually looks most like my larger kit here. This is a magnetic kit. I don't get any money from it, but they do sell them on Amazon. It's called, let me see here, Snatoms. It's expensive though. It's about $100. But if it's something that you're interested in, it's really good for demo purposes because they're bigger. What you could get, the school should have model kits. I haven't found them yet, but I will be looking for them. But these kits are much cheaper. You can get one for, I don't know, between $15 and $20 on Amazon. Just get the regular general chemistry model kit if you're looking for one of these. There's different types. You want to just have general chemistry basic kit. But anyway, that's optional. You do not have to buy it for the class. But that was our last type of model we see on this slide. On the right, we have a space filling. The space filling, as you can see, takes away the sticks from the ball and stick model because actually these are where the electrons live and they would overlap in this way. We don't see a gap between atoms that the stick shows. So this is an even truer model for a substance. Space filling. All right, here's conceptual conception connection number 3. Based on what you learned in the previous chapter about atoms, what part of the atom, I gave this away already, do you think the spheres in the molecular space filling models shown in table 3.1, which is the next slide here, represent? If you were to superimpose a nucleus on one of these spheres, how big would you draw it? So if you were paying attention, you would be able to answer this correctly. Take a minute, see what you think. Come on back. Okay, so my animation didn't come up on that slide to show the answer, so I will read it. So each sphere represents the hard outer shell. No, it's not a hard outer shell on the atom. Even though the model kit is a hard substance, that's not actually an atom. Let's look at B. Each sphere represents an electron cloud. The nucleus would be too small to see on the same scale. B is the correct choice. The nuclei, again, would be just very, very small. It may not even be able to be visible for the size of this particular model kit, and certainly not this one. So the nucleus is very, very small compared to the size of the electron cloud. The sphere does not represent the nucleus, so C is way wrong. Okay. This is the table that it referenced in the book for this question. So it shows you a few chemicals so that you could see how the structure changes to ball and stick, empirical to molecular. So they want you to just look for each row. And so I will, leave this here. You can pause the video and take a closer look for a minute, or you could take a look in the textbook. It's there as well. Oh, here's my answer. Okay, I stand corrected. All right. I had that table in between the two. All right, anyway. So here we are, an atomic level view of elements and compounds. So I really like charts like this. It helps with all the terminology we go through in the beginning of the course. So let's review. Elements can be either atomic, which they are just one atom per that element, okay? Or we could say an element is molecular, like a diatomic chlorine, or, wait for it, a diatomic hydrogen, or a diatomic oxygen. Okay? Carbon is not diatomic, so it would be just an atom. And so you can see on the far left there in blue, we have atoms. They're just singular. Molecular means there are two atoms stuck together, but still just one substance. Okay. On the other side, we have compounds, and both of these are under the main umbrella of pure substance. Okay? These are not mixtures. We have molecular, which is our covalently bonded water with two nonmetals, and we have our ionic, which is our crystal structure, where it's a ratio and it keeps building and building and building with that same ratio into a crystal form. Okay, so here we have the atomic elements, again, single atoms. It's a very short list here that they show for examples, but it's the majority of the elements on the periodic table exist as just atoms. The molecular elements, here you go. There's only 7. Okay, 7 diatomic elements. They're hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Okay, so if we find those on the periodic table, what we can do is we can color in, okay, where those elements are, and for demonstration purposes, it makes what looks like a number 7 in that right corner, and then just don't forget hydrogen over here. Okay, so other than that, I colored all the way down here. It doesn't mention astenine or tennessine because they're radioactive. They don't exist more than a fraction of a second. Anyway, I just colored the whole group. That's fine. Phosphorus and sulfur can also form polyatomic. Notice there are 8 sulfur atoms stuck together for this chemical. It doesn't always exist that way. And phosphorus is 4 atoms stuck together, which is unique. Okay, here's the picture I was referring to. Again, it makes that number 7, and here they used yellow. Don't forget hydrogen included for diatomics. I will just hold you to know the diatomics. All right, so let's take a look at this picture for conceptual connection number 4. Classify the substance represented in this picture by the molecular view that's being shown. What do you think it is? Okay, I'm sorry about that. So this would be an atomic element. That's actually incorrect. Let's fix that, right? It should be molecular element. Can you say why? All right, so atomic again refers to singular, one atom, where here we clearly see 2 spheres that are stuck together. And so that is going to be molecular, sorry. So this is a molecular element. The answer here is B, not A. Okay, so ionic compounds, to go back to this, we have, again, it's a metal and a nonmetal bonded together, which metals, when they give up their electron and become positive, the general term for a positive ion is a cation. The general term for a negative ion, which are our nonmetals, is an anion. The basic unit is not a molecule. We call it a formula unit because, again, a molecule refers to a small piece that exists on its own. This is a formula unit because it will keep building more and more ions coming into this structure and form a crystal as long as those ions are available and in that area. So because it can be whatever size, we call it a formula unit, not a molecule. So this is a comparison side by side of a molecular or covalent next to an ionic. Here's example 2 in your notes. Classify each of the substances as an atomic element, molecular element, molecular compound, or ionic compound? Okay, this is not multiple choice. They are 5 different questions. All right, so we're going to go through each one. Sorry, it's a bit wordy here. So xenon is just an element. It's group 8A, so it would be an atom, atomic element. NiCl2, so we have the periodic table. We would find on here, where is each one? Okay, nickel is a transition metal right in the middle, so he has that last name of metal. And chlorine is a nonmetal, so metal, nonmetal, it has to be ionic. Okay, bromine is a nonmetal, but it's in that colored number 7 we drew. So bromine would exist as a molecule, diatomic. That's on this slide. Okay. NO2, we have 2 nonmetals. Nitrogen and oxygen are both on the same side of the periodic table. So this has to be covalently bonded or a molecular compound. This is tricky. NaNO3, you see the N and the O together, which, yes, those do stick together as a unit, but this is something that we hadn't talked about yet until a little later. The NO3 exists as one big chunk ion. So it's covalently bonded in itself, but it has a charge. So we call that a polyatomic ion, poly meaning many atoms. So the NO3 is one unit that stays together, and the Na is sodium ion by itself. So this is an ionic compound because we have a polyatomic ion and a metal. That was a tricky one for you to get at this point. All right, summarizing ionic compound formulas. So ionic compounds always have a positive and a negative ion coming together. In a chemical formula, the sum of the charges of the cations must equal the sum of the charges on the anions. We hadn't seen that yet, actually, so we will see that soon. And the formula for an ionic compound is always a small whole number ratio of the ions. We hadn't really covered that yet either, so it's a little odd that the book puts this summarizing page right here. But we will cover this, so stay tight. So here we are. Formulas and names. Now we're going to get into naming. So remember we have the 2 different systems of naming. And so we have the one that just goes 1 to 18 straight across. However, I mentioned I like the older way, which is using 1A, 2A, 3A, all the way to 8A. And here's one of the reasons why. The A group elements, everything but the transition in the middle, okay? The charges that they become are predicted by those group numbers, the 1A, the 2A, okay? The A group elements always form the same one charge, okay? Transition metals, they're separated in that B group in the system that I like to show because they form multiple charges. For example, iron could be a 2 or a 3. So we need more information. So it's separated from the rest of the periodic table because of that. Okay, we can go through. Let me check and see if it's on a slide first. Okay. All right, so we have example 3. Write the formula for the ionic compound that forms between aluminum and oxygen. And so I want to add to my periodic table the charges for those A element groups, and I'll share it with you. Okay, I think I'll put an X there. Okay, so let's go through. So you can do this on your table as well. So I have group 1A. I put a +1 at the very top. All the elements in group 1A form a +1. Group 2A is a +2. Follow it across. Okay. You see, group 3A is a +3. Group 4 does not form ions usually. It can, but it's very rare. We'll keep it as an X as a no ion option. But then it's a turning point because after the group 4A, we start to go down to 0. So it becomes, we have +1, +2, +3, then we go -3, -2, -1, and finally 0. And so if we find aluminum and its charge that it'll form, oxygen and the charge it'll form, we could start to write a formula. And so in doing that, the first step is to write those symbols with their charges from their locations on the periodic table. Now I've also attached in this module a periodic table that has the charges and the name changes, because there are some name alterations to the elements depending on their charge. You'll see that if you study that periodic table, but it's something you can use to learn this with, and it'll be really helpful. However, on quizzes and tests, you will not be allowed to use that enhanced periodic table, we'll say. You have just the basic one. So you've got to know where the charges are so you can label it up on a blank periodic table, and a clean copy, not blank. And you've got to know the naming rules. So we're going to cover that. And so after we write the charges, we would then place the element symbols right next to each other, because we know formulas are written that way. And it talks about these ratios that you need to balance the charges out. So how many of these +3s do I need to balance out a certain number of -2s? Okay, there's an easier way to do this that works every time, and that's called the crisscross. The way the crisscross works is when you've written your ions, you take the absolute value, just the number. So aluminum has a +3. That 3 will travel away from the aluminum, and it becomes a subscript down low after that other element. In this case is oxygen. So aluminum's 3 becomes 3 oxygen atoms. Okay. Then we do the other ion. We move, again, absolute value. The 2 from oxygen's charge will go down and across and become the number of aluminum atoms. Okay, so here we have, we call this a crisscross. It works every time. Just the absolute value. The plus and minus do not go along for that ride. But now it says I need 2 aluminums and 3 oxygens, and this will be a neutral, no charge, stable compound. That's the idea. Okay, example 4 for you guys. Write a formula for the ionic compound that forms between calcium and oxygen. Okay, this one's a little bit trickier, and we need to remember that for ionic compounds, we always represent the formula as the lowest ratio we can. Again, ionic forms crystals, so it doesn't have a molecular true formula. It exists in any number of ions that'll keep building so long as they are around. So we use a ratio for ionic always. So we're first going to follow the steps from the last problem. We're going to write the 2 charges. And when you notice they're the same number, they're both 2s, they're going to reduce to be both 1s. Okay? We reduce 2 to 2 becomes 1 to 1. And so we get CaO as our ionic formula. This is any time the numbers for the charges, again, absolute value, are the same. So if I had 2 elements where one was a +3 and one was a -3, they're both 3, it would reduce down to a 1-to-1 ratio like you see in this example. Crisscrossing, and there we are. Okay. Naming. You might want to pause the video and stretch and take a deep breath, get a drink of water before we jump into this, because this is a whole nother topic. Okay, ionic compounds, as we see here, are a metal and a non-metal coming together. We have 2 different types that can form. One type is when we have a metal that is always the same charge. So type 1 refers to an A group metal. So that is group 1A, group 2A, or group 3A. Okay. The type 2 on the right is when the metal can form more than one type of ion, and that refers to the transition metals in group B. Okay. In addition to aluminum and boron in group 3A forming a +3, there are a couple other ones that always form one charge despite being in the transition metal group. I'm not going to hold you to memorizing these, but they are highlighted here. Silver is only available as a +1. Zinc is only available as a +2. And scandium only forms a +3. The other transition metals have at least 2, sometimes more possible charges. Again, you don't have to memorize those. You do need to memorize group 1A always forms a +1, and so on with the group numbers. Okay, so the way we name the anion changes. The metals do not change their name, but the nonmetals do. So let's look at some examples. When we have fluorine, when it's an ion, it's in group 7A. You wrote down that that forms a -1 charge. We typically don't write the number 1, so it's just the minus sign. Okay, the base name for fluorine is FLUOR, fluor. We're going to chop the "ine" off, and when it's an ion, it's going to be referred to as fluoride, IDE. So just me saying fluoride, you should imagine the F with the -1 charge. If I say to you fluorine, I mean the neutral fluorine, it's just the symbol F. Chlorine becomes chloride. Bromine becomes bromide. Iodine becomes iodide. Oxygen becomes oxide. Notice I don't have to change anything for the charge becoming a 2 now instead of the ones we've done before, because oxygen always forms a 2, so it's understood. Sulfur becomes sulfide. Then let's go to the 3s. Nitrogen becomes nitride, and phosphorus becomes phosphide. So the way we name these is we name the cation, which is whatever metal, and then we take the base name of the anion and put the IDE ending, and that becomes the name for our type 1 ionic compound. Here's a couple examples. So KCl is potassium. We don't change the name of our metal. Followed by chlorine, but here it's a compound, so it's an ion, so it's ide. So KCl would be written as potassium chloride. The next example is CaO. Calcium is the metal. The metals are always first, if that helps. Okay, so calcium is the first name. And then I have oxygen, but it's an ion to form this substance. So I have to say not calcium oxygen, I say calcium oxide. Here's one for you to try. All right, so let's go through it. So the cation is calcium. The name stays as is. The anion is from bromine, so it becomes bromide. They are 2 separate words. We write them calcium bromide. Also notice they're in lowercase. Okay, these are not proper nouns, so they don't become capitalized. Okay, type 2. A little more involved. So here we're going to talk about the transition metals in the middle of our table forming compounds. We have to be given more information to give it a proper name. And so iron, like I mentioned before, can be a +2 or a +3. And so we need to know what ion we have in a particular compound. We do a little investigative work to find out what it is. Here I have Fe and S. Iron is the +2 ion in this compound. The reason I know that is I know that the other element, the S, is always -2. It's in group 6. group 6A. That's always -2. Then we look at the ratio. I have 1 iron and 1 sulfur. So there are no 2's here, right? The 2 would have crisscrossed down, and it's not there. That means the iron must have been 2 as well, and then this was reduced to a 1-to-1 ratio. If you're not quite sure on following me there, it's okay. I do this visually in another slide. Okay. For this substance, the Fe2S3, iron is the +3 version, because if we undo this crisscross, that 3 after the sulfur came from iron's charge across and over on top of the iron. Okay, so because we know how charges become subscripts, we can undo that and we find out the charge of our transition metal. Copper, here I have copper 2. This one's always tricky because you have the 2 there, okay? Remember, oxygen is a -2, so that's where that 2 came from. Copper in this case has to be a +1 though. See how there's no subscript here? So they were different, or else they would reduce and go to 1's. We don't have that here. The next example we have that. Oxygen is always -2, so it would crisscross and there would be a 2 after the copper. Copper being a +2 would put a 2 after the oxygen. If they're both 2's, this compound would reduce to 1's, and that's how we got the formula CuO. I understand this may be dizzying. Believe me, after a few examples, you'll get it. Some of the main group metals like lead, titanium, and tin can also have more than one type of cation. For example, lead could be a +2 or a +4. Tin is the same way. Titanium, off the top of my head, because we don't use it too often, may have several different ions. Don't quote me. All right, naming these. We have to say what charge our transition metal has so we can distinguish it from another version, another ion type that metal can form. So we have to have a way to show what charge do we have in a particular formula. And with the name, what we do is we use Roman numerals to mean the charge of the metal. So we'll have the name of our cation. This is for when we have transition metals. The charge of that metal expressed as a Roman numeral, and it's written in parentheses. Then we follow up with what we did before. The anion has the "ide" ending. Let's look at this as an example. So for iron, we have the 2 flavors here, the 2 ions. We have a +2 and a +3 that are possible. And so iron 2 would be written as iron, and then the Roman numeral 2 is just the 2 lines. You can cross the tops if you want. That's a style thing, but you'll see it typed this way. And iron 3 will be 3 lines in parentheses. Again, they're capital here, probably because of when it was being typed out, just auto capitalized it. But again, these are not common proper nouns, so they can be lowercase. Here's a table in the book that goes through the rest, and these are the older names. You do not have to know those. See how it has different endings, and then that alone tells you the charge? You don't have to know that, but some bottles are still labeled this way if they're in the stock room. You won't be going in there anyway, but just so you know that exists. Okay, so let's do some practice. So we have CrBr3 and determine the charge on chromium. For an ionic compound, the total charge has to equal 0. It has to balance out, or else this wouldn't form. The whole idea is to balance. So chromium has to be a +3 because every bromine is a -1, and you're having 3 -1s here with that subscript. So you have a -3 with all the Brs. The chromium would have to be a +3 to balance that out. Okay. Again, you can think of it this way, or you could just undo the crisscross. That's the quickest way that always works. Just undo the crisscross. The 3 was up there. And so we'd have our Roman numeral 3, chromium 3, bromide would be its name. Again, there's a space right here between the words. All right, try this one. Okay, so on this one, that's lead. It may have taken you a minute to find them on the periodic table. And so lead would be a +4 in this case because the 4 subscript of the chlorine originated from being a charge on lead. So there it is. And so this would then have the Roman numeral for 4. And if you're not sure on what the Roman numerals are, I will always give them to you, but you should look through them. And as you do problems, you'll learn them. We only go up to 10, and even then, I'd say probably 8, 9, and 10 are very, very, very rare. 7 even is not that often either, and 6. So a lot of the lower numbers. Okay, so now we get to these polyatomic ions I had mentioned before. The video at the bottom, I've been showing my entire career of teaching chemistry. And so I found it very early on in my career. It's a very old video, but it works. There are a couple typos, and so I put them on a Post-it note. I'll just hold it up right now. The formula is written wrong for a couple of them, and then as you see on the bottom, those two substances are missing their charges. And so it's a student project, give the guy a break, but it's catchy. Years ago, I had downloaded it to one of my iPods, and no lie, jammed to it in my car. So even if you're not a fan of the rap genre, I think you'll find that it's rather catchy and it helps you learn the formulas with their names. So give it a chance, and who knows, you might be singing it next time we see each other. But polyatomic ions, so they're, again, a group of atoms that are covalently bonded together, but they are not neutral. They do have an overall charge. And so they stick together as one big ion, polyatomic ions. Okay. They have their own names to show that you have the polyatomic ion versus just the one element ion. And so here we can see NaNO2. Sometimes you'll have parentheses around the polyatomic ion. That's usually if you have more than one of that polyatomic ion in the formula. But if you don't have parentheses, a way to tell that you have a polyatomic ion that's there is that you have a molecule with 3 or more elements in it. Okay, if it's just 2 elements, you can't have a polyatomic ion. Okay, but if there are 3, you can start to look and see if you recognize one of the polyatomic formulas. Most of them are negative, so they'll be the right side of a molecule formula. Okay, there are a couple that are positive, and here's what we got. So take a look at this chart. The periodic table that I attached with this video in the same module that has the ion charges and the names also has a block in the very center up top that mentions these polyatomic ions. There are different length lists that exist. What I want you to focus on are the ones in red. You guessed it, you need to memorize these. I know we move very fast in this semester, but here's where that rap song really becomes handy. And flashcards, that sort of thing. You need to know the ones that are boxed in red. Their name, their formula, their charge. You must learn them. Okay, so here we are at example 7. Name this compound. So the first thing we're going to do is we're going to recognize, hey, I have 3 elements here, so there may be a polyatomic ion. And as you look, again, play your odds. Odds are the polyatomic ion will be the right-hand side of the molecule, so start looking at that end first and see if there's anything you recognize. This is a fairly uncommon one. This one's dichromate. So we find that polyatomic ion's name, and then we just name the other part. We always name the metal, then the non-metal or anion. So this one's name would be lithium dichromate. Okay, so for here, I added the formula for just the dichromate with its -2 charge. These are formed the same way. It's ionic. So that -2 would be up here as a charge. It would crisscross down, and that's why in the formula it's after the Li. Okay. These are certain polyatomic ions that exist in pairs where they are very close in formula and name. So I want to caution you and point these out. Okay, so we have a few pairs that do this. Two of them are here. We have nitrate and nitrite. Look at these formulas, NO3, NO2. Notice the charges are the same though, they're both -1s. Okay, look at the other pair, sulfate, sulfite. 4 oxygen, 3 oxygen. But they both have the same charge, -2s. Okay, the way you remember which one is which is the 8 name has more oxygen out of the pair. Now notice in this pair with sulfate and sulfite, the oxygen is 4-3, whereas the nitrate and nitrite, it's 3-2. So that you have to put into memory. But if you know that it's not NO4, for example, it's NO3, the 3 is the larger number, so that's the 8 version. Okay, now we're going to get into molecular compounds or covalent and how to name these. So these are not ionic, so we name them differently. There are no charges here. So let's look here. Nitrogen and oxygen can form all of the following unique molecular compounds. We can have NO, NO2, N2O, N2O3, N2O4, N2O5. They're all different substances. So we can't use the ion form of naming because these would all be named the same thing, nitrogen oxide. So there has to be a way to say one chemical versus another without writing the formula. And so here we do. Here we go. Here we do. I'm tired. So molecular compounds is when we have two nonmetals coming together. We write the name of the element with the smallest group number first. Typically, we write, the element that shows up on the periodic table to the left first, and then whatever's to the right of that element would be second. That's basically how it is. There is a little bit more science to it we're not going to cover right now. If the two elements are in the same group, then you write the element with the greatest row number first. So, periods. All right. Here's how we write these. We give prefixes to say how many atoms there are. And they're both nonmetals, so we have to say how many atoms of each are there. So the prefix will tell me how many atoms. Then we would name the element with that number of atoms. Then we would have a new word. This is not all one word. A new prefix to say the number of atoms of the second element. And we have the IDE ending again. Okay, there is a note here. If you only have one atom of this first element, we do not use the prefix mono. You just name the element. So let's take a look at that. Okay, example 8. Name each of these. All right, so there's a lot here. Let's go through each one. So the first one, we have a nitrogen and 3 iodine. So we need to say that. We need to say 1 nitrogen, 3 iodine. But the nitrogen is the first element, and there's only one atom. So we do not say mononitrogen. We just say nitrogen. So the first name is nitrogen, but then we have to signify that there are 3 iodine. So we need the prefix tri, and then we would put iodide, the IDE ending. We cannot say triiodine. That's incorrect. It's iodide, even though an ion is not forming for this compound to take place. It's the format of the naming. Okay. The second one, we have P, and this is Cl5. So we have chlorine and phosphorus. Again, we just have one phosphorus, so we're not going to use the prefix mono. We'll just say phosphorus is there. And then penta is the prefix for 5. So you're saying 5 chlorines, pentachloride. Notice the prefix means it's connected, so that's all one word. Okay, the last one is P4S10, so we need to say I have 4 phosphorus and 10 sulfur. The way to do that is now we need a prefix to say 4 phosphorus, so it would be tetraphosphorus, and then 10 sulfur would be decasulfide. Okay, One thing I also want to put in here as just a completionist, when we have double vowels like this, they're both I's, we tend to drop one, but I believe it's here just for the purpose of showing you the entire prefix there. So in other words, if I read this as it's written, it would read triiodide. The I stutter with the two I's is not correct. So we would drop the I of the prefix, not the element name, and this would be triiodide. All right, conceptual connection number 5. The compound NCl3 is nitrogen trichloride, but AlCl3 is called aluminum chloride. Which choice do you think is the reason why? Okay, so the correct answer here would be choice B. NCl3 is molecular because they are both nonmetals. Sorry. AlCl3 is ionic because aluminum is a metal, and so we don't need prefixes for ionic compounds. That's where this gets really tricky. All right, that's what we're going to do in example 9. Determine if each compound is ionic or molecular, then use the appropriate naming rule to name each of these compounds. All right, so we're going to go through each one separately. So the SO2, we're going to find them on the periodic table. We're going to say sulfur is in group 6A. That's a nonmetal. Oxygen's in group 6A. That's also a nonmetal. So I have a molecular compound. I have to name it using prefixes. That's the train of thought you need for this. So I need to say 1 sulfur and 2 oxygen. Sulfur is first. I don't use the prefix mono. Sulfur dioxide is the way this chemical would be written, and that name is at the very bottom of this picture here. Notice we have the double vowel here, but they're different vowels, okay? So we need to keep both of them. All right. The other one, we have COF2. We find these on the periodic table. CO is cobalt. Notice the O is small. Okay, so the second letter of an element has to be lowercase. If this O were uppercase, it would be oxygen, and we would have 3 elements here. We'd have carbon, oxygen, and fluorine. Because that O is lowercase, it goes with the C, and this is cobalt's symbol. Okay, so cobalt is a transition metal. Fluorine is a halogen, so we have an ionic compound. So we have to use the ionic naming. And further, cobalt being a transition metal, we need to say what type of charge it is in this chemical. So we have to undo the crisscross and see that that 2 with fluorine originated as cobalt's charge. And then finally, we need to say the 2 charge as a Roman numeral for cobalt, and its name becomes cobalt 2 fluoride. Okay. This is just a review of, the ones are not written for formulas. I just put this in here as an extra. You can pause it and read through, but we've covered this, I think, in depth. All right, so the last bit of this humongous chapter is a little bit of calculations that we need to do. Again, you're always going to be given these formulas on how to do this. You just have to know how to use them. And so the mass percentage of an element, we find the formula of the compound. There has to be a given mass analysis of the entire compound that we can break down into how much mass is contributed by each element. So it would have to give you data in the question for you to do this. Okay. Percentages may not always get 100% because, again, we have rounding with masses, so give yourself that leeway. But we have this formula to use. Okay. Without doing the calculations, take a look at this formula. Let me move my picture. C6H6O. Put the elements in decreasing order, so starting the highest, going to the lowest, mass percent composition. So what that means is look at the formula C6H6 and O. Consider the masses for each of these elements on the periodic table. Okay, oxygen is 16. You have one of them in this formula. Hydrogen is 1 each, and you have 6 in this formula. So that's less than 16. So right there, I have more percent oxygen than hydrogen in this chemical. Okay, and then consider carbon, and let's see how you do. All right, so if you chose that carbon would be the most percent in this chemical, you would be right. Okay, although oxygen has the higher atomic mass at 16 to carbon's 12, we only have 1 oxygen in this formula, whereas with carbon we have 6. So when you multiply 6 to the 12 for carbon, that far exceeds the 1 mass of 16 for that 1 oxygen. All right. We can determine a chemical formula from data. Of course, it has to be given. And we could be given the percent composition of each element, like we just did in our head there, or we could give the mass of the elements when we break the chemical down. I believe this second bullet point I removed from the chapter, so we'll stick to percent composition. Okay, really easy to do as long as you follow these steps every time. Let's go through the steps, then we'll see an example. You're going to be given percentages of each element in that formula. You're going to convert the percentages into grams because it's easier to work with that, and you're asked about finding the weight anyway, so we need it in grams to do that. Okay. So assume you have 100 grams of the compound. You'll see in the example, the percentages just become grams, no decimal movement needed. Okay, convert the grams into moles. We all know how to do that. And then write a pseudo formula. Pseudo is a prefix that means fake. So we're going to write like a fake formula using the moles as subscripts to give us a general idea of ratio. But then we're going to divide all the subscripts by the smallest number of those subscripts that we have. If the result's within 0.1 of a whole number, just round it. If it's not within that close range, there's a series of multipliers to get it to come out evenly to a whole number. And that will always be given to you. I'm not going to ask you to memorize that. I don't even have it memorized. All right, so let's go through an example and see how this works. This is how a question would be written. A compound containing nitrogen and oxygen is decomposed in the laboratories. We're going to break it apart. We're going to heat it up. It produces 24.5 grams of nitrogen and 70.0 grams of oxygen. Calculate the empirical formula of the compounds. Remember, we just want the whole number ratio of elements. We don't want the actual formula here. So what we're going to do is we're going to write down the given grams and then what we're asked for, right, to organize our thoughts. And then we're going to convert each of the masses here. We were already starting with mass, so we don't need to do the first step of the previous slides. So we weren't given percentages, we were going right to grams, so we're going to go right to moles. And here's what we would have. The 24.5 grams of nitrogen that was given, we're going to use the molar mass to convert it into moles. So 24.5 grams of nitrogen is equal to 1.75 moles. Okay. The 70 grams of oxygen that we got, we're going to use the molar mass here and convert it to moles, and we get 4.38. Now here's what we mean by the pseudo formula. We're going to take those moles and we're going to make them the subscripts. But you know that subscripts can't be written like that. We can't have a decimal for a portion of an atom. So we need to make these whole numbers. And to do that, we're going to divide by the smallest subscript. So out of these two subscripts we got, the 1.75 is smaller. So we're going to divide both of these numbers by the 1.75. And here it is over here on the right. So this is going to equal 1 with the nitrogen because they're the same number. The other one is still going to be a decimal. So what we need to do is consult this table that you will be provided and find the subscript 2.5. Let's see, fractional subscript. Okay, so we're going to multiply it by 2. Where am I finding that on here? Not whole numbers. Oh, we can multiply or use the chart. Got you. Okay, so if I multiply 2.5 by 2, 2.5 and 2.5 is 5. Another way to look at it, $2.50, $2.50, $5, right? So we can do that math simply enough. If it was more complicated, like you see these decimals, it might be harder to see how 33 would become a whole number. So that's where the table comes in. So the empirical formula then, now that we have whole numbers, would be N2O5. Okay, here's example 11. We've got experimental data here, and we're starting with percentages. So what we're going to do first is, see in red, assume 100 grams. This makes your life so much easier. So you have to say that you're assuming it's 100 grams, though. You have to write that. So part of your work would be writing, given 100 grams of this sample, 60% becomes 60 grams of carbon. Notice the zeros are all kept. Okay, that's precision. The 4.48% hydrogen becomes 4.48 grams hydrogen. And lastly, the 35.52% oxygen becomes 35.52 grams oxygen. And again, we're asked to find the empirical formula. So now that we have the grams, that step is over. We can continue where we were in the previous example. Use the molar mass and convert all of these grams into moles. And you see those are not very pleasant numbers. What's the next step? Pseudo formula, right? So we're going to just put those moles we calculated as subscripts for each element. Then we're going to see which one of these is the smallest number. It would be the 2.22. So I'm going to divide all the subscripts by 2.22. And we can see we've got a couple whole numbers, but the carbon's still not whole. Okay. So here we have a case where we have the 0.25. And so the chart says to multiply it by 4 to get rid of that, because that's a quarter, right? 25 cents. So 4 of them would make a whole dollar. So money really helps with decimals, I found. So maybe it'll help you. So anyway, so we end up with the 225. We multiply it by 4, and we're going to get 9 out of it. I bet you wouldn't have guessed that right off the bat, going from 2.25 to 9, right? No one thinks of odd numbers. But that helps you, right? The chart will always be given. So our empirical formula for this would be C9H8O4. We're almost done. You guys are such good sports hanging with me with this huge chapter. So lastly, we're going to get a molecular formula using the empirical and a molar mass. So again, you'll be given these formulas that are here. Let's put them to use. Butanedione, the compound responsible for the smell and taste of butter and cheese, contains the elements carbon, hydrogen, and oxygen. The empirical formula is given as C2H3O. The molar mass is given as 86.09 grams per mole. Now we want the true molecular formula. So in that case, we're going to write out what's given. We're going to write out what we need and what we know, the formulas, okay? The molecular formula is going to be the empirical times some multiple factor, which we're calling N. How do I find N? Well, it's going to be the molar mass over the empirical formula's molar mass. So we were given the molar mass here. We just need to add up the empirical formula to get its molar mass. Well, that's easy, right? We could just add up 2 carbons, 3 hydrogens, and 1 oxygen, and we'll have the mass of just the empirical formula to put in the denominator here. Okay, let's see that in action. So again, the 86.09 was given as the true molecular mass. That's the numerator here. Okay, we calculated the empirical formula, 2 carbons, 3 hydrogens, and an oxygen right here using the molar masses. And that came out to 43.04 grams per mole. This formula says the empirical's mass goes in the denominator. When we divide them, it comes out to a nice 2. So that means the 2 is our multiplying factor to use on our empirical formula. That was given, so we just multiply the given empirical formula by 2, and then our molecular formula is C4H6O2, the true formula for the chemical. Okay, you can double check your work by adding up the true molecular formula's mass, and it should come out to what was given. Lastly, we're going to talk about hydrocarbons. So normally this is a topic that is kept for the next sequence course. After Chem 1 and Chem 2, we have Organic 1 and Organic 2. And so I like to introduce it here because you've probably heard a lot of these chemicals already, so it'd be useful for you all to know. Now we're going to stick to just hydrocarbons. The functionalized groups, take organic if you want to know those. I cut them out of this chapter. All right, hydrocarbons, basically the short story is they're fuels. So we see them in oil, gas, propane, liquid propane for your grills, natural gas that you may be using in your home. They have their own naming system. And so a hydrocarbon is a chemical made up of just that, hydrogen and carbon only. So we call these generally alkanes when they're all single bond connected. Now carbon is pretty special because it can bond single, it can bond double, it can bond triple, it can bond to itself, it can bond to other chemicals. So there's a lot of variety. That's why this is its own class. So the molecule kit that I have here, the larger one, comes with these additional, they're like the bars for the other kit, the sticks. But these represent bonds. So this would show what we're calling a double bond, 2, to the same 2 carbons. Okay. If I fill this up with some hydrogens to, satisfy the bonds of the molecule, it would look like this. Sorry. And if I spin it, there are 2 hydrogens there. There's the double connection. We call that a double bond with carbon. And then the hydrogens. So we have 2 carbons here and 4 hydrogens. That's a double bonded carbon. These are called alkenes with an E in the middle when it's double bonded. Okay. If it's a single bond, I have to put another pair of hydrogen in. Okay. So now it's kind of hard to stick that together there. So now I just have one, I just have one connection in between the carbon atoms, this gray part. There we go, right there. Okay. And then I have 3 hydrogens on each carbon, right? So if I rotate it, you can see the 3 hydrogens there, and there's 3 on this one. So that's a single bond between the carbons. This is an alkane with an A. Okay. The last type is an alkyne. So that's a triple bond with the carbon. So that one's a little harder to do to get this to link up here. Let me just try. Ooh, it has to really contort to get it. I don't think it's going to go with this molecule kit. Yeah, it's not going to do a triple. They're too big. But we would have, so taking the hydrogens away, I can hold one in place. We would have 3 connections holding the carbons together. And it's not working because the carbons would have to be closer than they are, and they're already like practically touching. The ball and stick model would do it better. I don't have my carbons within reach, so we'll just go with the example here. It's a triple connection between the same 2 carbon atoms, and these are used with the Y and called alkynes. So those are the classifications, and it's by the bonds between carbons. Then we can say numbers, all right? Because we're talking about the carbons and how they're bonded, and then any remaining spots on the carbon that don't have bonds are just filled in by hydrogen atoms. We don't have to say how many hydrogens there are. Okay, so the number of hydrogens are going to be understood based on how many carbons we have and then how many bonds are in those carbons. That's how this naming works. So we're going to say 2 carbons and we're going to say they're double bonded with the name for this. So the way that's going to work is we're going to need to know these numbers. Do I want you to know these numbers? Yeah, I do. I do want you to know these. So go through the sequence, right? I'll do it without looking. Ready? Meth, eth, prop, bute, pent, hex, hept, oct, non, dec. Okay, you can do it too. You're just counting to 10. And again, the larger numbers we rarely see. So if you can get meth, eth, prop, bute, pent, you'll be in really good shape. Okay. Now meth, yes, it's kind of connected to the chemical focused on that show Breaking Bad. That is a much, much larger molecule, but slightly related to this prefix. Anyway, beyond the scope of this course. This is 2 carbons. So what prefix is for 2 carbons? F, right? So we say F for 2 carbons, and then we have to say it's double bonded. And so there we'll use one of these suffixes. Because it's double bonded, we use -ene. So this is ethene. Here's a chart that's in the book that goes through a few others. So methane, again in the molecular formula, or you can look at the structural, there's 1 carbon. 1 carbon is named meth. Eth is 2. Prop is 3. There are 3 carbons. Again, we don't name the hydrogens because they just fill in the gaps where the carbons aren't connected. Okay, these are all anes, A-N-E, because they're all single bonds. Okay, ethene, to form this ratio of 2 carbons and 4 hydrogens, the carbons would have to be connected double bond. And so that's the one I just built for you guys. Okay, and then ethyne, we have even less hydrogen. So why do we have less hydrogen? Because there are more bonds being taken up between the carbons themselves. And so ethyne is C2H2. Okay. Now there's a thing up here that says N-pentane and N-butane. So the N just means it's normal, which means it's a straight chain. That's more organic than general chemistry, but you can take off this CH3 here and plop it in the middle if you want. And that's how it can become a different angle. So that's what that means. And that's it. We made it. That's the end of this humongous chapter. Lots to learn. There's a homework assignment that's posted along with this. So try it over the next few days. Remember, you got to learn those Roman numerals. You've got to know your prefixes here. You've got to know whether something is ionic or covalent/molecular based on the elements that are bonding together. Lots of rules. Practice the homework. I may put up some additional stuff throughout the week so that you can try more examples. So be on the lookout for that. And of course, if you have any questions, send a message my way. Thank you so much for staying with me for this whole time. We'll see you in class.